Well, hello, everybody. Gather around. Throw a log on the fire. Let's tell a story. Have you heard about logarithms? No, not like this. No, not logs. More like this. Log ride. Yeah. Logarithms. Let me tell you the story. There was once an exponential. It's very powerful. The x's went into the exponent. So all these x values went into the exponent, and the graph grew so wildly. Exponential thought nobody could undo me. But there's something called inverses. An inverse can undo anything. An inverse, oops, that was a terrible way to do it. Let me try that again. An inverse is when we switch, right? Switch x and y coordinates and see what happens. Because if you think of functions, x goes in, y comes out. If you want to undo that, then y goes in. X comes out of the function. If we were to switch all of these x, y dots, they would be reflections over the y equal x imaginary line there. And that's what an inverse does. So when it was asymptotic with the x-axis, do you know what the inverse does? It's asymptotic with the y. Do you know when it hits the a value right there? No, it's going to hit the a value right there now. It switches. It switches. And this graph needs a name. We need to name this graph. It is the inverse, the undoing of the all-powerful exponential. This graph has an asymptote too. X equals 0 is the asymptote. So later, we can talk about graphing it. But let's talk about what this algebra does. And here's one of the main things I want you to think about. If x is the exponent, and we switch x and y now y is the exponent. Isn't that kind of cool? Because we just switched it. So do you know what all these outputs are? They're exponents. Logs, logarithms, not like the log ride at Disneyland. Logs, logarithms, they're the same as exponents. That's what they are. They're the undoing of exponentials. So it flips the x and y around. It's kind of cool. Logs can explode out at different rates based on the base. Not bases again, little 12 toes. Hang in there. If your b value in your exponential up here, if your b value in the exponential is big, then it grows fast. If b's 10, it multiplies by 10. So if our base is slightly different, then it can change. Do you know where the base ends up, that b? It ends up in this spot on a log symbol logic, on a logarithm symbol logic. See, we just flipped around x and y. No lie, we just flipped around x and y. Let's come back to this. Let's actually flip around x and y and now try to solve for y. So I would need to have the undoing actions to solve for y, and y is kind of up here in this exponent. Do you know what gets it out of the exponent? A logarithm does. And so that's how come logarithms came around. We needed to undo the exponential stuff that we created. And we used inverses. Let's take a look and see what logs actually look like. This is asking, this question in the homework here is asking, or this example is asking, hey, If your log is a base 2, if your log is a base 2, and you want to put in the value of 16, that's the input right there, what do you get for the output? What do you get for the output? And you can see in this example, they even wrote it that way. Y is the output. Now they do this cool thing of like change to exponential form. See how they have the notes on the side here? That's that European style again, isn't it? And so they're telling you the actions they're doing. They're changing this. And all of a sudden the y ended up in the exponent. This is the theorem behind it. I call it a circle trick. I circle around. So if y is in the box and I want to know what log base 2 of 16 is, I circle around. I say, well, 2's going to get raised to an exponent of y, and we want to know when that's 16. So we rewrite it. We go back and forth between the inverses here. I was in logarithm mode or format, and I circle around and I switch this to the same idea but exponential format. Now the theorem, they just give you the theorem. They say, well, the y goes up in the exponent and the number goes over here and the base goes there, and every time I teach it, students forget it. So you know what I do? I say do the circle trick. Okay? Write this down. To the y is equal to the thing on the inside. That's the trick. And then from there, you can kind of just see like at what exponent works. Like, does 2 squared work? Does 2 cubed work? Oh, wait a minute. 2 to the 4th works. Yep. That's why y is 4. That's why the output is 4. Here's another one. You ready? Log base 3 of 127. So this is what I would tell you to do. I would say circle trick it. Set it equal to y or question mark or anything. And this is key. From the base, circle around the equal sign and circle back to the inside. This is a cool little way to remember the theorem that they're just going to give you in a colored box on example like 2. I'm trying to give you a way to remember it. This trick, no lie, saves students in science class in college. They're like, oh, I forgot how to do this. And somehow they remember. Circle trick. And I know for a fact they don't remember the theorem in a colored box. That doesn't pop into their head. So you ready? 3 to what? Question mark. 3 to what? Is equal to 1 over 27. Well, I know 3 cubed is 27, right? 3 times 3 times 3. Yeah. How do I make it 1 over? Oh, wait a minute. I know. My teacher said it in the last period. Negative exponents make it 1 over. And that's why our answer is -3. Circle trick's kind of cool. That's one of the questions you'll get on the homework. The other question you'll get on the homework has to do with domains. So here's some sample problems of what you need to do on the homework. There's sample ones. This isn't all of them, but sample ones. And they want to know, okay, you ready? Logarithm, what's the exponent? 8 to what exponent makes an 8? I think you see that. 8 to what exponent makes an 8? I think we need a 1 there. So the answer is 1. 5 to what exponent makes 25? I have a feeling you might know that. 5, this is the idea of converting it to exponential form in case it's stated in the question. 5 to what equals 25? I think we know that. This is a 2. What is the exponent on 5 to make 25? See how that works? Trick questions. You ready? You ready? 2 trick questions here for you. 1/3 raised to what power makes 9? So, about winter last year, your advanced algebra teacher was slamming you with those exponents, and they talked about those negative exponents. Man, they're coming back and getting you right here. You ready? A negative exponent flips the fraction. So we need that 3 to get up to the numerator. We need to flip it. So let's make it negative. And then how do you make it? How do you make it a 3 go to a 9 with exponents? Squaring it. So this is a negative 2. Just so you know, that is an advanced algebra thing, okay? I don't think we learn it in algebra. When you see a negative exponent, that means flip it. So now it's 3 over 1. It really means 1 over, but 1 over flips it, just in case you didn't know that. And then if you square it, look, it's 9. See how that works? Okay, domain questions. Domain questions. Here's the deal with domain. Come back to our introduction. Look at domain here. Write this down for logarithm graphs. You don't have to graph these tonight, but you're definitely going to want to know how to do what the domain is here. The domain cannot accept any values, that are 0 or less. The graph doesn't exist there. The logarithm function does not like negatives, and the logarithm function does not like zeros. So let's go old school, like 7th grade kind of input-output function notation. I love factory stuff. There's a little sign here that says for all log functions, simple as this. For all log functions, x has to be above 0. That's what it is. So let's come over here. The way you answer a domain question is you take the input. What's this? ln. Ooh, we're going to have to come back to that in case you don't know that. Okay, you ready? The 2x, the inside of the log, has to be greater than 0. So this is like just doing the algebra that we did for domains of square roots, which had a similar rule. This one's a little bit trickier, and you're not going to have to do one like this, but I just wanted to show you that, you know, these rational functions can be thrown inside of a logarithm function, and boy, that's going to be interesting. One last little bit about logs. Logs can come in base 2. That means 2 to something, right? 2 to something, think circle trick. They can come in any kind of base. I've seen them in funky bases, like 2.1s and 1/3, as you see above. The most common one is base 10, okay? Not base 12, like little 12 toes, right? Base 10, and just so you know, they never put a 10 next to it. So the 10 is kind of invisible. So if you get a log without a number down there, it's a 10, because it's our base 10 log. And then there's a very cool log that happens in nature, and it uses the E natural number. This natural number is about 2.71. It's like pi. It's something that comes out in nature a lot. So guess what? Most logs you use in science class, they're called LNs. And it's really just log base E. That's all. Okay. I have a feeling you're going to be able to do some circle tricks and get out of this homework pretty fast. I think you can do that. Just one last one here real quick. 31. 10, circle trick, right? You getting the rhythm? 10 to what? Makes a square root of 10. Oh, if I only remembered my rules on exponents, then I would know that square roots come from fraction exponents, huh? Oh, the memories of advanced algebra just flooding in. Okay, I hope this helps. Good luck on the homework. Y'all have a great day.